Today I'm going to be talking about instantaneous rate of change. Now, what is instantaneous rate of change? It's basically something that tells you how the graph is changing at a certain moment. And that's kind of hard to imagine, but it is represented by slope of a tangent line, right? So let's say I have a curve like this. My slope of tangent line will maybe look a little something like this. And I'll kind of draw it clearly. And it only intersects at one point because by definition, that's what a tangent line is. And this tangent line represents this instantaneous rate of change. And it's kind of, you could think of it as the velocity of my curve, the way the curve is going to move at that certain moment. It is basically when I move a tiny nudge in my x value, what will happen to my tiny nudge in y value? And I'll give you a more mathematical definition for instantaneous rate of change, and it might become a little clearer. And it basically says, well, we know that slope is delta y over delta x, right? Now, what we want is our delta x to be very, very small, right? So let's say I had a curve like this, and then I'll use a different color. Hold on, let me get blued. And I'll call this point x. And I'll call it f at x for its y value. And I'll call this point x plus h. And h will be the distance between my x values. Or you could think of it as my h is my delta x, right? And my y value would just be f at x plus h. Now, what happens when this h approaches 0, right? Let's take a look what happens. If my h approaches 0, then my tangent line will kind of approach a closer and closer accuracy to my tangent itself, right? Like, let's say my h value was super large. Let's say it was this big. Right now, let me reduce it a bit, and it becomes this big, right? And let me reduce it even more, it becomes this big. And at this point, you can see that it's pretty much accurately representing the tangent slope, right? So you could think of this as, hold on, x and f at x. And then there's just a tiny little nudge here. And we'll call this x plus h and f at x plus h. And we want this h to be like close to 0 as possible. It cannot ever be 0, and you'll see why algebraically. But what happens is if we want to represent this, we'd say, okay, what's my delta y? Let's just take this value. Let's that be y1. So it's y2 minus y1 over x2 minus x1. My y2 is f at x plus h, and my y1 is just f at x. And my x2 is x plus h, and my x1 is just x, right? So you'll see that my x's cancel out, and I want h to be equal to 0, right? Or close to 0 as possible, right? So in the end, it goes like that. And then this would equal to f at x plus h minus f at x divided by your x's cancel out, so we're just left with h, and limit as h approaches 0. Now, the reason we can't have h equal to 0 is because we'll divide by 0, right? And my top would just be f at x minus f at x, which would equal to 0 over 0. But we can't really do that mathematically, so we represent it as limit as h does approach 0. So that's just a brief introduction to instantaneous rate of change. I'll do some examples later on.